I think I can go on. Good morning, everybody. Can you hear me? Okay. Yeah, it's my great pleasure to introduce this morning's speaker, the CAIMS Research Award for the year of 2024. Okay. Which is who is Dr. Wang from University of Alberta. Okay. Professor Wang received her PhD from Arizona State University in 2006. And then after 2 years postdoc at Georgia Tech, he went to University of Alberta for a faculty position. He's now a full professor and also is a CRC chair, tier 1 professor at the University of Alberta in mathematical biosciences. Okay. Dr. Howe has been very successful in attracting research funds and has received millions of grants from all levels of government as well as from industries. His research areas is wide, covering from ecology, including animal movement, and also especially biodegradation, and also modeling and analysis of ecotoxicology. Particularly, it is for his outstanding contribution in applying the stoichiometric theory in mathematical modeling and analysis of biological systems. He was nominated for this year's CAIMS Research Award, and he has been awarded. So, Dr. Al has been also successful in training HQPs, has trained a large number of HQPs, also has been published a large number of papers, I think it's close to 200. So his outstanding contribution in the stoichiometric theory in mathematical modeling, including environmental sciences, and it was very influential. And so I think today he's going to give a presentation summarizing his research in this area. Okay. So I pass the floor to Dr. Wang. How you can go? So the floor is yours.
Yes, good. Yeah, thank you very much, Professor Xin Zhou, for the nice introduction. And thanks to, I also would like to thank Suen and Felicia for arranging my talk, because it's a bit hard, because I tried to attend the conference in person, and because I had some prearranged travels, including the one SMB meeting in Korea in a couple of days. So I think Suen suggested probably it's to give the talk online. Yeah, I really hope I can be there in person. Yeah. And it's my great honor to receive this CAIMS Research Prize. And thanks to the committee for selecting me for the award. And the talk is about stoichiometric theory and its application in methane biogenesis. So that's about biodegradation. Of course, this work had a lot of contributions from my HQP and collaborators. You will see in the talk. And but before I start, I would like to mention some challenges in mathematical biosciences. So first one is the mechanistic modeling by fundamental physical and chemical laws. So stoichiometry is a good idea. Okay, it's a good approach to do this, but not the only way, of course. So it's always challenging, right, if we want to have robust modeling. So, and the second part is the true model validation and the comparison. And we have seen all kinds of overfitting. And we had a theorem to show that all kinds of overfitting in the model validation when we use data to check model. If we have so many free parameters, we may have overfitting, right? That's a very common issue. And here, instead of the theorem, I'm going to show one simple example briefly, and to show that can we do solid model validation without many freedoms, right? So that's the example I'm going to show, the biodegradation case. And the transient dynamics versus asymptotic dynamics. This is a natural topic because almost all math tools are developed for asymptotic dynamics. And However, in reality, we may need transient dynamics for from some important phenomena, right, that we cannot characterize using symptotic dynamics. And unfortunately, we don't have many tools to analyze transient dynamics. So uh, we know that in applied side, we have more and more people interested in this, but we have not much tool, right, to use for this transient dynamics. I'm going to show one example, okay, for symptotic dynamics and how we deal with like transient dynamics as a natural comparison. And we work on all kind of applied problems, all levels like government, industry, partners, biologists, right? Or we even design our own experiments. But we still hope from all applied problems we can have helpful or useful feedback to the math society. So probably we can develop novel mathematical computational methods through applied problems. So that's would be ideal way, right? But not always working that way. And in the past decade, we have known big data and machine learning, AI have been fast growing. Right? So it's hard to avoid that. I think it's very helpful if we want to use tons of data, right? Integrate that with whatever model we have. We may need some statistical and machine learning approaches to be integrated into the approach. So that's still in progress. I will mention a bit about the machine learning as needed, but I'm not going to show the integration of them. So I think my team has made some efforts in this integration of different approaches in the past decade, I think, this direction. But that's not the topic of this talk here. It's just I can claim in the end as future work. Okay, a bit background about stoichiometry. So normally we use these two examples. One is kind of different light intensities, right? For plants, basic producer, and herbivores, consumers eat them. And the other example is a competition of two definite species, right? So first case, we see that as light increases, we have more and more algae, right, measured by carbon or algal carbon. However, herbivores cannot survive with a lot of food available. So the mechanism or the controlling factor is this kernel with bubbles. Have in highlight, we have fairly low nutrient content in algae. So the curve with circles for the algal PC ratio, phosphorus content, right, in algal cells. So it's kind of the last case in extra highlight. Definitely have a lot of trash food, so they cannot survive. Of course, you can imagine classical predator-prey model cannot describe this, or produce a greater model cannot describe this. So it seems like we need another dimension. And the bottom one is experiment done many years ago, and it's a competition between highlight, just between two species, on the highlight and low light. So limhozai, the tiny here, is the invasive species from Africa to North America, and Purex is a native species of Daphnia. So if they compete, we can see in highlight, we have invasive species excludes the native species, right? The low light is opposite. Native species excludes invasive species. So we had some modeling work together with the data to explain the exclusions, what's the mechanism, and also possible coexistence. Can have very complicated chaotic coexistence in this case. And the highlight, low light, if we look at these jars, we can see just the jars without black cover, the low light, and the jars with black cover, the jars without black cover highlight, the jars with black cover, a low light. See that from the picture here. And of course, all other environmental conditions are controlled in the lab. Right? The only difference is the light test. We try to use these to motivate the stoichiometry because the classical models cannot explain these phenomena. If we look at different species, why people always use Daphne as the study species for stoichiometry, because this guy has high phosphorus requirement. So we can see 80 carbon need one phosphorus. Other species have lower requirement phosphorus. So if a species selects to have higher phosphorus, then it has some advantage in growth rate. So the condition is good. then that species has higher nucleic acid contents and can grow faster. So that's advantage. But if phosphorus is very limiting in the environment, then that can be very negative. They can be easily restricted by phosphorus. And if we look at these two equations in the bottom, looks unfamiliar. They look unfamiliar, but actually we are familiar with this. First one just photosynthesis. So just autotroph plants consume inorganic matter and light and produce more plants and exude some whatever the elements they don't need, right? And we use prime on the right, just meaning this XY decomposition on the right different from XY decomposition on the left. So there can be huge variation of the elemental composition in autotroph. I will mention that point again later. And the second equation here is predator-prey interaction. So we're familiar with predator-prey, right? Many people here have worked on at least predator-prey models, right? And normally just population, right? So here we consider predator-prey in the elemental composition, DMP, right? Predator consume prey and prey is gone. Predator can produced. Either they grow up larger or they give next generation and they exude waste in some composition to keep the balance of element composition. You see that we don't have prime on the right. So left and right, this elemental composition of CMP for predator is the same, right? Side. So of course, we can write out equations, right, for these processes here. Of course, it's very easy to make a mistake for this kind of model. You cannot easily add a term, move a term. Normally it's wrong. And the fundamental reason is obvious because all organisms are composed by cells. So what's in the cell? So CMP obvious what they're doing, right? So damage and the protein and nucleic acids, so they are key elements for those. So as I mentioned, the first example I mentioned, first experiment data I mentioned in the beginning, right, cannot be explained by the classical predator-prey model because those models just consider models only consider like carbon flow. Normally we call that biomass population or density, right? So cannot explain that. So we need additional dimension, right? So because it's just introduction, I don't put equations, but I just claim that if we add the dimension of the nutrient and keep track of the nutrient contents in plants, then we are going to get some new dynamics which can explain that experiment. So the first three cases as light increases are consistent as classical predator-prey model. So we just have starvation, right? Plants have low quantity and the predator cannot survive when light is low. As light increases, we have coexistence, right? When we keep increasing the light, then we have hopification, which generates limit cycle, right? So these three phase portraits are the same, right, as the classical predator-prey model. But if we further increase the light, with the nutrient dimension, we have something new. So this E4, the internal equilibrium, this is new. Okay, this guy is stable. Have bi-stability of the limit cycle here and also equilibrium. So that's kind of new. And if we further increase the light, then E4 will be globally symptotically stable. So all solutions tend to this internal equilibrium. Finally, solutions critical bifurcation E4 disappear. E4 and E1 collide. So we get a stable boundary equilibrium, which means herbivores cannot survive, right? Daphnia will go extinct with a lot of food available here. So that's consistent to the Daphnia extinction. I think that's a simple example to motivate the necessity of the stoichiometric, right, operation. We can also plot this phase portraits as a bifurcation diagram here, right? We can see by stability region, right, of limit cycle and internal equilibrium E4, right? So if you have interest, you can look at this paper for all theorems, okay, for the bifurcation to be generated. Yeah, so actually I plot this bifurcation by hand, almost by hand, because we know all possibilities to mathematical analysis. Not hard to plot this figure. And you see that in this bistability region, right, we have two attractors. So later we also worked on a stochastic version for the environmental noise, how that drives the possible transition between different attractors. So you can use confidence ellipse and the confidence band to describe the possibility of the stochastic transition caused by environmental noise. These are the two cases. And if we compare the competition, this elemental competition in Earth crust and in human body, we see a big mismatch. So if we look at the percentages of carbon, phosphorus, nitrogen in human body, they are much higher than percentages in Earth crust. So this kind of shows living organisms make a very discriminating selection elements from the environment, which is not good, right? Which is not good. So which means we can be easily limited by these elements, right? These elements make that selection. There are a lot of stories we can discuss under this and also this periodic table of the elements. Okay, so for modeling, we need some fundamental laws, right, to help us. So one is the conservation of matter. We learned this in high school, right? So before and after chemical reactions, you may have different forms of molecules, but uh, we have conservation of each element, right? So that's for normal chemical reactions. That's so you can use that either to simplify the model or to check the model is correct. If we have after chemical reactions, we have any loss of element, we need to ask where it goes, right? Where is it? And leaving soil minimum is kind of a barrel rule. It's kind of the water level is determined by of a barrel is determined by the lowest side. Logically, it sounds reasonable. Just the growth rate of organism is limited by most limiting element factor. That's kind of the leaving soil minimum. You can use if we have multiple factors, multiple elements. And Gibbs form is developed for the growth depending on intracellular nutrient contents, right? So it's actually more mechanistic than the growth depending on the external nutrient using monodiform. So we had a review paper recently. I will show you in the next slide for comparison. So if you work on any resource-based growth in any model, maybe you want to be aware of that comparison. And Lambert-Beer's law, we use this to, this is just physical law, right? We use this to describe the light intensity along across water column. Of course, this normally need to be modified by the absorption or reflection of living organisms, right? Like phytoplankton in water. And homeostasis, I wrote these two papers, try to show that when this strict homeostasis assumption works, when it does not work. So the logic behind this is normally people assume heterotrophs have strict homeostasis, which means their elemental composition stay the same. Okay, and for autotrophs like plants, they have huge variation of nutrient contents. That's the common sense, and that's normally true, right? Normally true, but actually there's still a range of variation, maybe small variation of elemental composition in heterotrophs. Whether that will cause any bifurcation or any dynamical change, then that's a discussion in these two papers, just to show when that assumption works, when it does not. And here's the work, the review I just mentioned. We compared the Monod form and Gibbs form. And that's pretty interesting because biologically just this figure, right? Monod form is a simplification of Gibbs cycle. And we started with group statement, a personal email to me, and also the paradox here. So I think it's interesting to see the logic behind this. So we have conservation law, right? And if we ask this simple question, almost naive question, is more nutrient available in media good or bad for algae? So monodiform just says good, right? Because algae have more food to use, right? Have more nutrient to use. But if we use the conservation of matter, we know if more nutrient in media means less nutrient in algae. So that's bad for algae. So if for the Gibbs form, it's opposite. So we see that sometimes these two forms will give opposite results, right? But on some assumptions, they are consistent. Okay, they will give same results. So I think in this paper, we try to compare mathematically and numerically, and in the end, we just summarize the scenarios when we can use monod, which is consistent as Gibbs, when we cannot. I think it's interesting if you work on resource-based growth modeling. And I want to introduce one example here on stoichiometric modeling. I didn't show any equations yet. Right? So this is one example I show. I think it's just one simple case, but still not that simple. We just I will show you the aluminum case, top layer. Quickly were mixed overnight. So we can use integration to simplify the story, exclude the spatial structure like a PDE, right? But if we model the bottom layer hyperlinear is present, so more or less we have to use PDE, right? And the four lake model has been done years ago, right? It's, my former PhD student Jude Kong and some colleagues. So yeah, by the way, Jude, I will mention Jude's work again, another work on that biodegradation. And Jude is a faculty member at the University of Toronto now. Yeah, so that's the full model. Okay, that's the full model for this one. So I don't expand the details for that full model here. And here I just show you the top layer. Top layer is illustration of the modeling concept. Of course, this is a very old work, right? Like 17 years ago. So 19 years ago. So if we look at these variables, AQP, so A is Lg measured by carbon, Q is cell quarter, or you can call it phosphorus carbon ratio. It depends on units, right? If A measured by carbon, it's phosphorus carbon ratio. If A measured by number of cells per volume, then it's kind of the phosphorus per cell, right? Depends on the unit for A. And the dissolved mineral phosphorus, it's a P, right? P is dissolved mineral phosphorus, which can be used by algae. And if you look at this simple model, we see that the gypsum 1 minus Qm over m. Q little m is the minimum cell quarter. So, cellular nutrient dependent growth. And this is the light intensity dependent growth. So we have the I light intensity described by Lambert-Beer's law. It's modified by the absorption by phytoplankton. And KBG is background light attenuation coefficient. Little k is specific light attenuation coefficient by algae. And we use this light uptake efficiency take integration over space divided by the length of the depth, right? So Vm is the depth. So just take average, right, using mixing assumption. And here we use modified Lebesgue law minimum. We can use minimum function of these two growth efficiencies, or we can use multiplication as a smooth, you can say as a smooth interpolation or smooth like approximation, right, for the Lebesgue law minimum. And this is respiration loss because A is measured by carbon, and when they do respiration, CO2 is lost. So just keep track of respiration loss. And this V plus D over dm just the sinking and the water exchange. And the phosphorus consumption by algae described by this, and kissing is this rho here, which is the per unit consumption rate, right? So this is also replenishment rate of cell quarter. And rho, the key thing I want to describe is this capital Q, when the cell quarter reaches maximum cell quarter at 0, they stop uptaking nutrient. That's reasonable, right? That's a cap. And when Q reaches minimum cell quarter, it's 1. So this uptake is strongest. And this is dilution due to cell division or algal growth. So looks like this very similar to the growth term, slightly different. The capital rate is the same. So the growth rate divided by A, or this dilution rate divided by Q is the same. So the idea is one cell divided into two cells without nutrient uptake. Then each cell will have half of the nutrient. That's kind of rough idea. And you can check the conservation laws. Kind of A times Q is the total phosphorus in algae, right? So if you take derivative, use the product rule, these two terms should be canceled. Because one cell divided into two, the total nutrient is the same. Okay, so this in DT we have some kind of looks like thermostat stuff, right? Because we have input, output, right? And preliminary, and we assume the volume stay the same. So this kind of a simple model, right, for phytoplankton. The reason I show this because I want to show something about the transient dynamics. Yeah, so we can get a group of nice theorems using monotone dynamical system and to show global stability stuff for monotone dynamical system, right? Because it's complicated, but it's a competitive system, right? So that's done many years ago. And mathematically, it's interesting. Scientifically, it loses the key feature about algal bloom because why we study algae. So we care about algal bloom. So that's the next story I'm going to tell. So it's about Chinese dynamics motivation here. This work was done by my former PhD student, Chris Heglood. He was jointly supervised by my colleague Mark Lewis and me. And yeah, so he will be a faculty member at the University of Manitoba, I think soon. And we can see these different stages. So this is just a simple solution curve, right? It's very simple solution curve. So we want to see some idea from here. So A is still algae, right? Measured by carbon, Q is cell quarter, and P is without phosphorus. And we can see stage one, abrupt uptake of P. We can see that it's completely a different scale. Immediately, this nutrient, the cell quarter shoot up to max, right? Maximum. Whereas that takes no time, right? So it's kind of another, it looks like in a very fast dynamics scale. And light limited bloom stage. So that's the blue case, the blue one. So the blue curve just means limited by light, and the red dotted part limited by nutrient. So we can see kind of bloom here, which is limited by light. And then we have crash, right? Crash of this bloom, right? And in that stage, we have nutrient limitation. Eventually, it goes back to the low algal density case. So of course, cell quarter or dissolved phosphorus we never observe, but this algae we observe. That's we have a high density, we see the bloom, right? The dense your lake, right? And however, asymptotic dynamics cannot show us anything. We start from low, we end at low, right? So we don't really catch this important phenomenon of algal bloom. That's the Chinese dynamics. Yeah, so that's the effort we make in this paper here. So first step, so because of time limitation, I may not go through details. So A, Q, and P, right? I just copy paste those three equations. And AQ is a cell is a nutrient in algae, and P is a free nutrient. Together is a total nutrient, right? Total phosphorus. So we can convert this P equation to the S equation, then do the non-dimensionalization. Right? Then we can obtain some kind of small parameters. So here delta is kind of singular parameter for perturbation, and beta is kind of regular perturbation parameter. Right? And we can discuss fast dynamics and slow dynamics. Right? So for example, for fast dynamics, do transformations, tau equals delta T1, and let delta goes to zero. It's very easy to get this. Okay, so just from here, right? Take this transformation and take delta goes zero. We can get this result. Of course, we can see that this means U is a constant and W is a constant. So U and W both constant, right? So we can see that for equilibrium case, just be either one or the other case W over sigma U, right? If Y is here and W over sigma U is here. And depending on initial condition, we can have different possibilities. So solution can either tend to W over sigma U or tend to. And the slow dynamics can simply take the delta goes zero and beta goes zero, right? So we can see this slow dynamics, and we can see important manifolds, critical manifolds from second equation, right? So V zero equals to this right-hand side. We can just solve this, and we get either V equals one, or we get this the other case, V equals W over sigma U. So we have these two semi-manifolds, and we can plot them as M00, the purple plane, and M01, the pink surface here. So on the purple plane, we have sufficient phosphorus, but light limiting. And in the pink surface, we have sufficient light, but the phosphorus limiting. And double L just means fast dynamics. So we just put some examples, some representative solutions, right, to show the possibilities. So we see that these two blue ones, these two solutions never tend to this purple plane. They just go up and go down, then to low level, right, for algae. And if we look at these two black ones, we see that they will tend to this purple plane and will stay for a while and then crash, right? So we try to explain the mechanism of algal bloom, like if the solutions can stay on this purple manifold, submanifold, then uh, we have bloom, right? And we're able to estimate this longevity, right? How long the bloom will stay. And if we have this blue case, if solutions never stay around this purple plane, then no bloom. So that's kind of the mechanism we try to explain algal bloom. And we can estimate the longevity like, in different ways. We can even write up explicit formula under some assumptions or simplifications. So biologists can use the formula to estimate the duration, right? Time duration of bloom if it occurs. And of course, we want to also compare whether the Bayesian system is a good approximation for the original system, right? So this is the comparison we have, and also we apply the Finiture's theorems to show that's indeed a good approximation. And this is a story just for asymptotic dynamics and transient dynamics, right? So sometimes transient dynamics will be the key to obtain the main interest, right? Main focus we want to figure out. And still, you can criticize this because we have considered nutrient and light as key elements or key factors. Why that? Why that? Maybe not. So if we consider all possible covariates, for example, lake features or the landscape, right, around the lake, or the atmospheric conditions like weather conditions, right? So all kind of covariates can be considered. Yes. Beforehand, we don't know which one is the key, right? Just guesstimate. Right? So we have uh, long-term monitor data from about 7, 8 lakes in Alberta over decades, and we also have tons of covariate data. So in this paper, we use machine learning to handle all those covariates and try to uh, forecast the probability of blooms, right? In future, normally next 2 or 4 weeks, right? 2 to 4 weeks. And the orange ones just show the high probability and the corresponding key factor, right? Guiding that. And the blue ones just mean low probability, right? So it's interesting. If we use the machine learning, we have no limitation, right, on how many factors we look at, right? Of course, the original factors in the data sheet we have much more than this, right? So we exclude or clean up the data, just exclude some obviously unimportant ones, right? So we put what we think most important ones to look at bloom probability. And we also plot this from the Bayesian network approach. So these blue guys just mean key, you can say main calculates, right, or the key factors for the target. Target is algo blue. White ones are less important. That's the rotation of this graph. Yeah, of course, this is based on the conditional probability, not the purely causal results. Okay, so that's use of simple use of machine learning, right? As I said, I don't explain how we integrate the AI machine learning with classical models. That's important effort we are making past few years. Okay, then we apply this idea to this methane biogenesis. I think only 5 minutes left. So I'll quickly go through this. So this is data for greenhouse gas emission in Canada. So Alberta has, I think, over years, we are more dominating than Ontario. In 1990, Ontario was more dominating. So we're increasing, especially for methane release, we are probably more dominating. So because methane is the more uh, harmful greenhouse gas than CO2, right? Than carbon dioxide. So that's why now we have more focus on the methane emission production, like estimation, right? And also the forecasting, and as well as mitigation, right? You can see the overall Canada, we have some peak, right? 2006, then we have some policies to drive it down, right? Similar for Alberta, right? Similar for Alberta. And we expect to keep decreasing this methane to keep decreasing in future, but that's just some conceptual like expectation, right? Well, we have three main goals. The first goal is we try to accurately estimate methane production, which is important for for the carbon tax collection and the future planning, right? And the second goal is we want to understand the impacts of key covariates on the methane production. And the third goal, we want to test strategies and policies, right? Methane control. And this kind of forecasting, which is important to reach the global mitigation of greenhouse gas. those vehicles. I'm not going to resolve that here, but just give you a bit of effort and also the future plan. So this is study area in east, like northeast Alberta, right? The mining regions, and we can have this rough picture, okay, for the biogenesis process. Of course, in the first model, Jude did just for the beginning and the end. Okay, so we're working on more mechanical model now, but this the one I show here, just a big simplification. The key idea is from this chemical reaction. Okay, so these hydrocarbons, this CCHH, the little c, little h as two integers, right, which will be used to compute this stoichiometric conversion coefficient, which is gamma I, which is this SFI here, right, this formula. Then integration from 0 to t summation is for the I, right, for the I. So if we have n hydrocarbons, then we just have accumulation of the methane production hydrocarbons. This is kind of a simple stoichiometric model, right? Using conservation of carbon, conservation for this nutrient, nitrogen here, right? And okay, so probably need to skip this. So we collect the samples from the field, right? And we have different groups of the degradable hydrocarbons. Of course, some hydrocarbons are non-degradable, recalcitrant. Those cases then takes a very long time or forever to decompose. So normally we look at biodegradable ones, which includes maybe 40% or 60% of those compounds. And we can use lab experiments to measure degradation, those coefficients for each compound. Then that will kick out the freedoms of parameters, right? And in this paper here, we do the data fitting, but we have these estimated parameters, right, from the biodegradation in the lab. And if you have interest, you can read this paper for details. And we compare this the so-called stoichiometric model with the previous models like zero order, first order. Sometimes they are consistent. All of them can estimate the mass production well. Sometimes can be off, like those first to zero order. This here is the case. First order can also be complete off, right? So that's different examples. We can use statistical comparison, right, to normalize the mean square error, right, to compare these models. Okay, and recently we are in this awarded Encircle CRD project. We had measured like different temperatures, right? How those difference, right? Different temperatures affect the biodegradation and the methane production. And because the paper not out, so I don't put the results here, but I just mention what we are doing. And in the reality, of course, in nature also have some variation of temperature, and it varies over seasons and over depth, right? So it's interesting how we connect the lab measurement experiments to the field data, right? Or field methane emission, right? So that's a challenging question. We're making effort at direction. And in the recently awarded Circlines missions project, it's awarded last year, and we expand more possibilities like different nutrient situations, right? And how that those control the methane production and biodegradation, right? Those things. Yeah, so I think we will keep expanding these treatments. Okay, second year now. So this is I think from the first year. So we are going to expand more possibilities for the second year and look at more covariates and even look at other gas production, greenhouse gas production, not just the methane. And okay, this one not published, so I cannot show you how we get it, but I can explain why we do this here. We want to check whether the reported methane production from each company are accurate, or they are underestimated or overestimated. So we use model to check that. Of course, if there's big mismatch, maybe it's a model problem or maybe it's a reporting problem. So we need to figure that out. And we think that's important for the carbon tax and also for future planning. And in addition to the station's aerial data, we also have used the satellite data. Satellite data will have some disadvantage because it's not accurate, right? It's vague. But the advantage is it has huge scale and a lot of data, right? So that's the big advantage. And we use some machine learning approach, right, to try to predict methane concentrations from different directions, right? So we consider those wind stuff, right? So we incorporate all kind of information, try to understand the kind of movement of methane and the production of methane, right? What's going on exactly in the air. So, again, it's not published, so I don't give details about how we get it. Okay, just briefly mention our efforts ongoing. Some take-home messages. I think it's about the time. So I just to quickly show that this stoichiometric theory can be useful, right? Mechanistic modeling and Chandelian dynamics can be significant, okay, even though we can only deal with symptotic dynamics using math proofs. And true validation, I just want to show the example with almost no free parameters to avoid the overfitting, and that's a more challenging validation. And all kind of approaches like non-smooth systems, monotone dynamic system, perturbation theory, machine learning, or integration of these approaches. I don't mention that here, but that's in progress and would be an important development in future. And for greenhouse gas emissions, that's a very big and important topic. It's a global environmental problem. How to estimate that, control that, mitigation, future planning, blah, blah, would be important, right? So that's still in progress. And in the end, I want to thank all collaborators for these the papers or the projects in this work presented, and all existing local members physically in at U of A in my lab, and all supporting grants to my team and projects. Like thank all of them. Yeah, so that's the end. If you have questions, you can ask me.